All right, yeah, thank you, Alex, for that introduction. Yeah, so just a quick description of what I'm going to be talking about today. I'll provide a quick project description and talk about the leak localization methodology that I've developed. And then start to pose the question on how we should be measuring accuracy for leak localization. And this can depend a lot on the different types of models that you're developing. And then I will pose the solution of using the maximum coverage location problem to reduce the search area for secondary leak detection crews to pinpoint the leaks. And then just quickly talk about the results and next steps. Just a quick overview of the two projects that are working on this that I'm working with is the Fireway for Water project, and specifically working with the Water Network Management Smart Data Model, which is integrating the EPA net into a smart data model that we can integrate and change individual components and help with the calibration process of the detection models. And then there's the Aqua 3S project, and that's specifically focusing on the algorithmic advancement of detection and localization of events within a water distribution system. So here's a quick overview of the model that I developed. There's three submodels, which is typical process in the burst detection. And so here we have the anomaly detection. And so this would be when you feed data in. If there's an anomaly, it triggers an alert. This alert then goes into the second module, which is the anomaly localization. And here it tries to find the location of the anomaly. And then that is fed into the intervention management model, which is focusing on trying to develop solutions to mitigate the impact of that event. And just kind of briefly talking about the calibration process, first it's a model-driven calibration, but then as we collect more and more data, this can be recalibrated on the real data and the accuracy improved. So the presentation is specifically going to be focusing on the anomaly localization model. And I don't want to get into too much into the details of the actual development of it, but quickly just simulate first, it's a comparison of a no leak scenario with a leak scenario, calculating residuals, and then developing some form of machine learning model to predict where the leak is occurring. But I think the question that is often maybe sometimes not necessarily posed is how do we measure the accuracy for the burst location? And I think how you answer that, it might sound like a pretty simple, straightforward question, but slight differences in how you answer that can have an impact on what type of models that should be chosen. So if you think about accurately identifying this specific leak node within the water network, you might think that the classification model is probably the most appropriate. But instead, if you're looking at minimizing the distance error to the actual leak event, then you might want to look at regression models where you can predict the XY coordinate of the actual leak. But often what happens is that if we're not dealing with very, very high frequency sensors, or if the sensors are sparsely populated throughout the network, there's going to be some need for a secondary leak detection, pinpointing of the actual leak within the network. And for these people that are doing the secondary leak detection, reducing the search area is very important. And so when thinking about the accuracy or the objective function of the model, we should be trying to reduce the search area for the leak detection crew. And so how do we figure out a way to reduce the search area using the localization model? And I pose this in a question in how do we determine the ideal search area that covers the largest probability of leak location within a specific area. And one of the solutions that I think that would apply in this case would be the maximum coverage location problem. This is an old, relatively old computational problem that was invented back in 1974, and that's gained a lot more traction now in a lot of geographical-based solutions. And so here, this model might look a little bit difficult, but what it is you have if you use a machine learning model to predict the probability of a leak occurring at all nodes, that's a simple classifier model, since it puts out 0 to 1 probability for those nodes. Then what you want to do is maximize the coverage with a specific area. And so here you can see the two circles, and these would be possible areas of the centroid of the circle, and a specific coverage radius. And so the maximum coverage of these nodes of leak probability would then be the ideal search areas for the leak detection crews. The one thing to mention here that those aren't going to be double counted, it would be the total coverage for the search area. So I wanted to see if this maximum coverage location problem would be effective in reducing the search area required. And so I applied this to a case study. This is an EPA network, but using the smart data model to simulate the variety of leaks and to train the data set. And in this case, we had simulated 13 sensors with 15-minute increment readings. And so here are just the overall results. And so what I wanted to do is say, okay, what kind of search area is needed to capture, accurately identify or accurately capture? And in this case, I said 50% of the leaks, but we could have picked a different value, and the area would just have to increase or decrease depending on it. And so I wanted to compare the more traditional models, such as a classification model and a regression model, to the maximum coverage location problem. And so what you can see here is, okay, for the classification model, in this circumstance, I would pick the node that it predicted that the leak is occurring at and expand the search area out until it covers 50% of the leaks within the testing data set. And so there's the classification model, has one of the largest areas that are required for the search area for the secondary leak detection crew. The regression is a similar approach. It has the XY coordinates that it predicted. We expand the search area out until it captures 50% of the leaks. And then there's the maximum coverage location problem, both with one search area and two search areas. And I also compared it with a hierarchical clustering model. And what you see here is that the maximum coverage location problem actually reduces the search area significantly compared to classification model by about 50%, and with the regression model by about 35%. And this is for one search area. If we start to expand it to two search areas, this reduces the search space significantly by 80%. Of course, there's an added cost if you're sending two leak detection crews out to pinpoint the leak, but this could be a very big benefit if you're trying to reduce the time to find the leak event. And again, then the last thing to just mention is that it outperforms the hierarchical clustering model as well. So that's kind of just sped through all of that, but in the end, I think that when you're developing these detection models, sometimes the end goal of how it's going to be used is somewhat lost in the typical accuracy metrics that people look at. For example, looking at the AUC or for a classification model or reducing the mean error. But I think when developing these, you got to look at the accuracy in how the utility will be using it. And often in cases where we're not having really high frequency sensors, the utility will still require pinpointing of the leak through the leak detection crews. And if that's the case, then we should be trying to reduce the search area. And if we're trying to reduce the search area, I think the maximum coverage location problem is one solution. I'm sure there's a variety of clustering solutions that may do comparable results. But the maximum coverage location problem also has the advantage of being very customizable, changing the number of search areas that you would prefer, or search radius. If you wanted to capture a certain percentage, this can all be adjusted depending on the utility's preference. And then just the next steps for this research is to optimize the search grid and to improve the search time, because currently this is taking a bit of time to search through all possible search areas. And then to integrate these results into the intervention management model so that we can mitigate the impacts of these leak detection, or these actual leaks or bursts that are occurring in the network, and mitigate those impacts to the customer as well. And then lastly, to apply these to the case study with live sensors. And that's it. Thank you.
Thank you, Brad, for your interesting presentation. I can imagine there are some, I think also very interesting for utilities to all over the world to reduce search areas when you have leaks. can imagine there are a few questions from the audience.
Thanks for the presentation. I was wondering, are these leak detection methods already applied widely? And what are the biggest challenges when applying such methods? Is it about data quality or transparency, or could you?
Yeah, I think that there's two main parts to that. So there's the leak detection from the algorithmic standpoint. And so that would be the important part, is having the data and accurate data, as well. Having more sensors in the network is always great, but the sensors cost money. But then from the pinpointing of the leak with the leak detection crews on the ground, there's a variety of techniques that they can do that through correlation methods, removing temporary sensors that can also improve the search area.
Jan Peter already got a question, so I'll come to you first. Ladies first.
Well, thanks for the presentation. I was wondering if you also look at data anomalies and how to detect those in your algorithm.
Yeah. So right now, just working on the pipe burst anomaly, so looking at that. But then if you look at the anomaly detection, the model that I've developed is using like an exponential weighted moving average. So that just helps be quicker. So it's not an actual machine learning model. It's a little bit quicker in that regards, and doesn't need as much training.
Okay, see Jan.
Well, a short question. You already answered part of it. Optimization, that's about the number of sensors in your system, but also the localization of the sensors. So where you place the sensors, that has a big effect on can you really locate bursts. Is that also part of your research?
Yeah, that hasn't been yet, because the utilities that we're already working with is already putting in sensors in their desired location, or they already have them there. But that is definitely an option, and it makes a huge impact to reduce and improve the accuracy of the localization model.
Yeah, I have maybe for a last short question, a bit in the same direction, is that you used flow sensors and pressure sensors. Yeah. Usually there aren't that much flow sensors distributed in the network.
Right.
Did you also try just with pressure sensors and no flow sensors?
Yeah. So I've also done some comparisons looking at what sensors actually work better. The pressure sensors aren't as effective. The flow sensors are a little bit better, but not substantially. So the pressure, if we just had pressure sensors, it would work close to being the same.
Thank you. Well, thank you, Brad. So give him a